the best way to learn it is get right on it. So anyway, before we go into antenna modeling, my slide rule instructor tells about age. My slide rule instructor at El Camino College, when calculators were first becoming legal tender, he made a great quote. He said, "A calculator is a machine that will give you the wrong answer to 15 decimal places." So nothing could be more accurate than that. So you better know what the answer is going to be before you give it to a computer. One of the rules of thumb we have when we do antenna modeling is if an antenna model surprises you, it's probably wrong. So you should have a pretty good idea what an antenna is going to behave like before you put it together, and then you can confirm it and tweak it up a little bit with some good antenna modeling program. Let's see. We may get to the point sometime where you have good enough artificial intelligence that you can say, okay, this is my property I've got. Will you please tell me what's the best antenna for this situation? But in general, you have to have a pretty good idea of what you've done your research, what kind of antenna you have or are capable of putting together. And then you can use the antenna model, you can confirm it. It saves you a lot of cutting and trying. But antenna modeling should always be an iterative process where you model it and then you build it, and then if it doesn't work right, come back and model again. So you should be able to don't rely entirely on building an antenna from a model and going out in the field. Well, before we go into actual antenna modeling programs, I want to talk about a very popular antenna and why it can be kind of troublesome. Anybody here have an EFWH or end-fed half-wave or end-fed horizontal wire? Okay, how many know that they can be very touchy?
Really?
So it's very popular antenna, very convenient, but it's got some issues. Now, part of the reason is you're feeding an antenna at the end, right? And what do we know about the end of any wire and when you're doing an antenna? It's going to be very high voltage, right?
Yeah.
Very high impedance, very high voltage, okay? It's not going to match 50 ohms. So what's the normal solution to what do we normally need to add to an end-fed horizontal wire?
Transformer.
A transformer. Now, what does a transformer do?
Changes the impedance.
Changes the impedance, okay? However, as we will show, it does absolutely nothing to fix the reactance. So we have this very interesting little chart here, and this is an ARRL handbook, and it's been in every edition for years. What we're doing is we're showing the impedance of an antenna, both the reactance and the resistance, as we sweep it across a wide range of frequencies. Now, an end-fed half wave is pretty much the same thing as a center-fed full wave. So an end-fed half wave will always be an end-fed antenna, whereas if we take a dipole and just feed in the middle at its resonant frequency, it'll be a low impedance. As we increase frequency, you become higher and higher. But anyway, let's look at some interesting things here. Here's a sweep here. Can anybody see that? Okay, yeah, I got it pretty good. I might just expand it just one more here. This is a plot here showing the feed point impedance versus frequency for a theoretical 100-foot long dipole in free space, fed at the center of an extremely thin wire. So what we have here, if we follow this line here as a frequency, here's some nominal frequencies around here. So what's the horizontal axis? If you're using a VNA or whatever, what do we know happens at the midline, at the equator here? That's resonant points, okay? So if we start at some very low frequency and move up here, we have our first resonant point, and that's at 5 megahertz on this 100-foot antenna, theoretical. And we notice there's kind of a gradual increase of radiation resistance. Now, the reason this is not a spiral like you would have on a VNA is because these are logarithmic scales. If these are linear scales, this would pretty much be a spiral. But it's kind of compressed, but that shows very dramatically what the issue is here.
What's the left axis there?
Oh, left axis, this is reactance.
Oh, that's reactance.
This reactance. So minus 7,000 ohms up to 7.
Frequency?
Well, the frequency is following along here. So frequency is 1, 2, 3, 4, 5 megahertz. These are megahertz.
Okay.
Yeah, these are megahertz. And then this is real resistance.
That one's labeled.
Yeah, that one's labeled radiation. It is. I had I was supposed to get the actual software from the new AWL antenna book, but it was not available yet, so I had to photocopy this, so forget that. Anyway, so our first resonant point is at 5 megahertz, and we know at this point, by definition of resonance, we have no reactance, and it's a pretty reasonable impedance. It looks like it's about 100 ohms here, nothing too radical. As we increase the frequency, we come up to this point here, and where it crosses the axis coming down. What do we call that? Now, this point here, where this line is following down and it crosses this axis again, but it's moving downwards. Now, those of you who've been around a long time, back in the broadcast industry, we call this anti-resonance, which I actually like the term for it. It's actually parallel resonance officially, but we always use the term anti-resonance. And the reason is what direction does reactance go as you move up in frequency? On your normal resonance, we're going from inductance. Inductive reactance is, capacitive reactance is anything below the horizon. Inductive reactance is anything above that. So in going through our normal resonance, or series resonance, our reactance goes from capacitive reactance to inductance. And then we come back down here and it's going the opposite direction. And so we're going from inductive reactance to capacitive reactance, so the direction has changed, so that's why it's called anti-resonance. Now, what do we know something about here? See, this is kind of a gradual increase as we go through our series resonance. What do we have here? We have this absolutely precipitous change of reactance from a very high value between 9 megahertz, 5,000 ohms of inductive reactance to about 5,000 ohms capacitive reactance over a very small frequency range, okay? This is our anti-resonance point. These are what you want to avoid, like the Ebola virus, if you want to make an antenna that's broadbanded, okay? So yeah, there's a very dramatic change of reactance. Now in the third harmonic, this is why a 40 meter antenna works on 15, right? Because we once again, we're at third harmonic and we have a rather gradual increase and we have a normal series resonant mode and the impedance is reasonable here. And then as we go to the fourth harmonic here, again, we have this precipitous change of reactance between here and here. Now, when we build our transformer for our EFWH antenna, or EFHW antenna here, we normally pick like, who actually has one of these transformers? What ratio are you using?
We're using a 9 to 1.
9 to 1, okay, which is actually kind of small. Some of these guys 16 to 1. So it really depends on the height of the antenna. But in any case, even it's always going to be a compromise. So you've already narrowed your possibilities of frequency range by virtue of the fact that we have so much that depends on the height and everything else. But also, the transformer does nothing to address this sudden change of reactance, right? Transformer will give you the right resistance, but all your reactances are transferred right through that transformer. So if you got a touchy antenna, it doesn't matter how well you match the thing, it's going to have a dramatic change of reactance here. So we have a paradox. We always call it a half-wave resonant antenna, okay? But we want to avoid that resonance, okay? We want to get away from that. You want it, if it's possible, to be on the left side of there. Now, what's the earliest half-wave antenna going back historically, 100 years? A ZEP, right? ZEP antenna. And what was a ZEP antenna fed with?
Ladder line.
How long of a ladder line? A quarter wave, a Q section, which means that anything that you had a very high impedance here, but that quarter wave section brought it over to the back to the low impedance side again. But it only does that one frequency.
Right.
So the ZEP antenna and a J-pole is nothing but a stretched out ZEP antenna. You have the same thing. You have the quarter wave matching section, which is feeding the end of a half-wave vertical antenna. So right off the bat, we see we're going to have some issues here when we're building an end-fed half-wave wire. It doesn't mean it's not a good antenna, and the resonance or lack thereof has absolutely nothing to do with the radiation efficiency. This is one of the big misconceptions, is the fact an antenna has to be resonant to radiate. It has nothing to do with how well the resonance. It does have something to do with how well you can feed power into things. So we want the antenna, the system, to be resonant. Doesn't mean the antenna itself has to be resonant, but we have the system. But be aware that if you're building one of these antennas here and you say, well, gee, I've got all these nice commercial, whether power ends or whatever, the commercially available end-fed half-wave antennas, things is awful touchy. Well, all the press doesn't tell you anything about what's happening over here. And we'll do some demonstration of a VNA, not in this particular antenna, but just some general rules for using VNA. Now this chart's modified a little bit for actual, rather than extremely thin wires, using moderately thin wires, 0.1 inch. And so we don't have quite the extreme excursions here. The fatter the antenna is, generally you'll have a little bit more broadband. And then we have, this is feed point for a 100-foot dipole in free space fed at a center of thick 1-inch diameter wire. So this would be more applicable with a Yagi made of antenna thing. So anyway, I don't mean to pick on the EFHW antenna, but this is one where probably antenna modeling is going to give you the most insight right off bat. So let's talk about antenna modeling programs. I really like this program. It's called 4NAC2. Most AWL handbook centers on EZNEC, and I do have EZNEC on here as well. But this has some really neat features that EZNEC doesn't. The disadvantage, though, this only works with NEC 2 engine. EZNEC is now available with the NEC 5 engine. So if you're doing like large surfaces or highly tapered elements, NEC 5 actually is a little better. But NEC 2 is good for 99% of what we're going to be doing here. So this is, it's called 4NAC2, and it's available, it's all free. It's amazing the free software is out there. So 4NAC2 is a program of my preference, and so what we do here is once we have this thing open, we'll build an antenna from scratch, and we'll start with something that we know, okay? We all kind of know what a dipole is supposed to look like. Okay? Anybody done antenna modeling already? EZNEC? Okay, now you have. Okay. Yeah, okay. So what we do here is, first thing we need to do is get to our main screen here, and what we're going to do is create a new file. So we go to Edit and a new input file, and then we go to our construction screen here, and we'll start from scratch. We'll put a new file here. So what we have is we have three different views. This is our normal XZ view, which I use most of the time. And this is your Z-axis, which is up and down, X-axis is left and right, and Y is in and out toward you. And we can also look at this directly from straight overhead. If it doesn't lock up here, okay. So here's our XY view, and Z is the axis coming toward you, so we're looking down on an antenna. And the YZ would be looking at like the end of a dipole. And then you can also look at the whole thing in 3 dimensions. So first thing we need to do is we need to tell this thing what frequency we're using. So we go over to this frequency here, and it defaults to 299 megahertz. So we'll use 7 megahertz is a good frequency to start with. So we have 7 megahertz here. We'll go back to our original construction. And what we do is we add a wire. So we have a wire here, and we hit add, and we simply drag and drop. So here we have an antenna, okay? Now, I have my units set in actual physical feet. You could change the unit lengths to be in wavelengths, which for some things is very convenient. But we'll use what we know. Okay, so how long's a half-wave dipole on 40 meters, 7 megahertz, about?
65 feet.
Okay. So we'll put 65 feet. It automatically generates it. So what we can do here, let's zoom this out a little bit so this is all on screen. And what we can do here, we can center this. So we can take the arrow and we can grab this and we can center it. Or if we want to get really pedantic about it, what we can do here is we can select the wire and we can put minus 33 feet here. And then we can do the other end is 33. That'll exactly center it. Now, we're missing something, and those are our segments. So the way numeric electric code works is it chops the antenna up into a bunch of equal length segments, and then it treats each of them as if they have equal current across each segment. And so what you do is we hit segments, and this will locate them. So now we have these alternating segments of green and red. And the reason we generally want to center this as well as possible on our screen is so that we can place our feed point or drive accurately. So this is our generator here, and we want to put add. And what we want to do is we want to drag it across the center of the antenna here. And if we do that right, we have a little dot there. Okay, so that's our generator. And we can either use a current generator or a voltage generator. If you're building phased arrays, you always want to use a current generator. And we won't get into that probably today. But for certain types of antennas, especially phased arrays, you're more concerned with the current than the voltage.
Now, I know you didn't want to get into it, but can you give us a summary of why?
Basically because when you have a phased array, you have interaction between the antennas. You have mutual coupling, and that can change the impedance and the current phase dramatically. Whereas voltage, we just assume that the antenna is going to have the voltage, whatever we're putting in there. But anyway, we're going to start with a voltage source here. And then what we do here is, we need to determine ground. So we'll put this in free space. We'll show you what the ground does later on. But right now, we select this as free space. So here's our ground condition. And we hit the little calculator here, and we're looking for a far field pattern. Okay, what's this thing going to look like? And again, we start with something that we're familiar with. That's our sanity check. And then we say, okay, this looks kind of like we would expect it to look like. And we do generate. And lo and behold, we have an impedance here about 65 minus A56. So he says 65 feet is actually closer to 66 feet, but we'll show something that's really cool here. So here's our radiation pattern here, and this is looking broadside to the antenna. We can change this to looking at the end of the antenna. So the end of the antenna, we know it's going to be a wire in free space. It's going to be perfectly circular. Or if you want to get really fancy, we go to the 3D view here, and we can go to the pattern, and lo and behold, here's our classic donut shape for our dipole. Now, the reason this thing's poking through the middle here is we did not put this at ground level. When we start working with grounds, this will make more sense. So let's show what just having a ground does to a dipole. So let's put this up at we'll close this out, and we'll change the height of this a little bit. Let's see, what is our height? Our height is our Z's over here, so we're only at 16 feet. So let's see, let's make this a quarter wave high. So we'll put that at 33 feet as well, both ends. And we'll put a perfect ground under this thing. Now this has all sorts of choices for the ground. So if we go to real grounds here, we have average ground, we have all this other stuff. We even have Arctic land, which is nice. And we can have either a near ground or a far ground. So you can have the extended ground here. So the second ground, because how many are aware that the ground conditions of an antenna far, far away from your antenna can actually make a difference? Okay? When you start working DX, you may want to be 100 wavelengths away to really define things. So this will go out maybe 10 wavelengths here on the real ground. So we won't use the extended ground at this time. But let's put a perfect ground under here. So let's see, here's a perfect ground, assuming the earth is paved with copper, okay? Now we have really lousy grounds here. Most of interior Alaska, you might as well be in free space. You know, I've had an 80-meter antenna fall down in the middle of winter. I never even knew it. It worked just as fine lying on the ground. So anyway, let's calculate this again. Run through a calculate, far field pattern. And lo and behold, we don't have anything below here, right? Everything's above ground, okay? And we can go to our 3D view again, and go to our pattern. And lo and behold, our donut has now become more like a kidney bean here, okay? We're missing our really nice dip in the middle. But you notice also at ground, at horizontal, we have a perfect null going out horizontally from this, okay? Now, we won't normally have that kind of a condition in interior Alaska. What we'll have more likely is a lousy ground, okay? So we can pull out a lousy ground. So we'll change this to a lousy ground, And again, feel free to stop me at any point here. So we'll go to real ground here, and you can use average or what's Arctic land. Yeah, I might as well do Arctic land. Okay, about as bad a ground as you can have. So let's change the shape quite a bit. Okay, our null isn't quite as wide down at the bottom. Okay, going back to 3D view. So now it's no longer quite our kidney bean shape. It's squashed out a bit more. Okay, we still have a null at ground level here, but most of our radiation is about 35 to 40 degrees.
So is the antenna the line that's showing on the?
Yes, here's the antenna here.
So why isn't it centered on the antenna?
Yep. This is a quarter wave off the ground. Yep. So if you have perfect ground, what happens to the gain straight up if you have perfect ground as you decrease the length of the height of an antenna?
Say that again.
What happens to the field strength straight overhead as you lower an antenna, assuming you have perfect ground?
Oh, it increases.
It increases toward infinity.
Yep.
But why can't you take advantage of an infinitely low antenna and get infinite gain?
Reality.
Yeah, what is the main reality?
It's going straight up.
No, it's a DC resistance or skid effect resistance.
Okay.
If we had superconductivity, we could do that. But there's a diminishing point. It's about 1/8 of a wavelength where the losses of the ground system and your antenna start equaling the the gain of the antenna. So somewhere between 1/8 and a quarter wave, we actually have well, I should say for what we're doing at high pass down in Wyoming, we were trying to get maximum strength upward. We're using between an eighth and a quarter wave. Okay, let's go back to perfect ground here. And again, most of this, if you played with antennas at all, should be pretty intuitive. We shouldn't have any real surprises here. Again, if you're seeing a real surprise, your program's probably wrong. So let's go to perfect ground again, and let's put this at a half wavelength. Okay, half wavelength high. So we'll grab this here, and oh, there we go. We'll grab a wire if we can. There we go. And we'll go to 60. Oh, we went over here. 66. There's our z-axis over here. Okay, we can zoom this out a little bit so we can see it. Okay, oh no, not that high. Okay, and we'll calculate this again. Okay, so we have kind of a null overhead, okay? We do have a null off the side here. We have two lobes here, which can actually be pretty useful here. Let's see, we were 6 halfway. Okay, so let's go to a full wavelength over. So let's go to 132 feet. And let's see. And computer. That's really high, yeah. Okay, and we can zoom this back down. I don't do it. You can also do yeah. If you need to move this around, use the right click on here. Okay, so now we can do this and far field pattern again. And you have quite a few lobes there, okay? And we're going to have a lot of angle. Typical DX is probably going to be coming this angle, so it's not going to be really good for doing a lot of DX. Ground level's not here. So maybe some really low angle DX here. So anyway, again, this is over perfect ground. Now let's go back to a lousy ground and show what that does. Generally, the as a general trend, the worse your ground is, the shallower your nulls are going to be, and you'll also lose some gain in your lobe. So it's going to be the closer and closer approaching an isotropic radiator. Everybody know what an isotropic radiator is? You all know a light bulb, okay. So let's go to real ground here again, and pick something different. Here we go, the mountain, up in the mountains here. Okay, so we no longer have a super sharp null over here, and we don't have quite as many little spikes here, okay, so it's kind of smoothed out the radiation pattern.
What's the feed point impedance of that going to be?
Oh, yes, the feed point impedance is still about 50 ohms here. Yeah, 65 ohms here. Yeah, we'll go back to that. Okay, so, there's a pattern. Kind of a neat looking thing. Now, here's something that's really surprising. Let's see, magnitude. Okay, can anybody guess what these colors mean?
Phase.
Yeah, well, yellow is your linear polarization areas. Pink is clockwise circular polarization, and blue is counterclockwise circular polarization. So except in free space, even a dipole has directions where it's going to be circularly polarized. Pretty cool, huh?
Yeah, that's interesting. I've never seen that actually modeled in that way. And that could be a good thing.
It could be a good
the
thing.
Angles of arrival,
Yeah.
especially here,
Yeah.
are always changing.
That's right. That's right.
And the polarization.
And the polarization. Yeah. Well, yeah. Well, you stand off. What if you're intentionally trying to do that? What's the best way intentionally creating circular polarization? What's the simplest way?
Phase two dipoles.
At right angles, a turnstile. So why don't we build a turnstile here? Okay. So we'll go back to, and we'll use these at, we can go to free space again. This is pretty much a half wavelength. So what we want to do here is we want to look at this thing. How can we do this? So it gets a little tricky to not overlap it too much here. So let's see. Yeah, let's do this. So we'll add a dipole just slightly underneath here.
So Eric,
Yeah,
does that apply to reception as well? or
absolutely.
is that only
Everything's
transmission?
reciprocal. That's the beauty of all this. Reciprocity is. The only thing that's not reciprocal in your topic is the ionosphere. But in line of sight propagation, reciprocity is king. So let's drop that down just a little bit. Let's see, 130, 127.5. Let's make this 127.5. Okay, now we have to also put a generator on that one as well. So we'll zoom this in a little bit so I can do that without overlapping. Where'd it go? Come in, computer. Okay, let's grab this here, bring that down. And let's see. Zoom one more. And we will add another generator. And we'll do that right across this guy here. Okay, now, to get the phasing right, what we do is we're looking at our generators here, and we actually have our source here, so we can switch between here. So let's make these current sources. So we'll change that to a current source, and we'll change the other one also to a current source. and we'll change the phasing, the relative phasing. So this one here is at 0 degrees, and this one here is also 0 degrees. Let's change one of these to 90. And now you can express it either as imaginary numbers with a real and imaginary root, or just the amplitude and the phasing. So we have 1 ampere at 90 degrees on that feed point, and 1 ampere at 0 degrees. For a sanity check, we can go to our 3D view, make sure these aren't overlapping here. They're spaced a little further apart than I want, but sometimes when you get closer together, it's kind of hard to do without them. But we should be able to get a pretty nice circular pattern here. Far field pattern. And, let's do this in free space, because that's going to mess things up a bit. So let's go to free space. Okay, and calculate again. Okay, so this is looking at one end, the other should be pretty much the same thing. And then we go to 3D. Okay, so here's our patterns, almost pretty much omnidirectional. They'd be much closer if I had those antennas really, really close to each other. But this is what we really want to look at. We want to look at the sense. Okay, so turnstile. In the plane of the turnstile, it's omnidirectional, but linear polarized. As you come straight overhead, it's either going to be clockwise or counterclockwise. So this is your typical turnstile antennas is what you have here. So now we can have, there's also, what can we show here? Axial ratio. This shows you how circular it is compared to, when we talk about circular, and the ellipse is actually, or a circle's a special case of the ellipse. So this tells you how circular that circularity is. With the red is perfectly circular, and as you get away from that, it's less and less. Let's see, a couple other things we can show.
Just to kind of add, if you're working, say, in satellite communications or something like that, the axial ratio can be rather important in performance of your system, because typical satellite downlinks are circular. So anyway, it matters.
Yeah. At HF, it's noticeable. Not so much the axial ratio, but between clockwise and counterclockwise, it could be typically, on a single hop, it could be 3 S units difference between being matched polarization and unmatched, Jim Movius and I did a lot of experiments, so that was just pretty dramatic what that is. Another thing is very interesting, when you're listening to auroral noise is circularly polarized. You can see a big difference between X and O propagation and listen drawer. Chad, long time no see.
This is a question we get in the satellite world quite a bit. What is the point of circular polarization? And the thing I want to emphasize, and your program might be able to show this, is that if a satellite with normal monopole or dipole elements is tumbling and radiating at all kinds of different angles continuously as it comes along, then circular polarization is a really good thing, because matter what, you'll never get worse than 3dB of whatever the satellite is doing when it's coming down. Where if you're doing something linear and the satellite is broadcasting, you can get some deep fades.
Yeah. And some people confuse Faraday rotation with circular polarization. It isn't. Faraday rotation is slow, but it's still linear, whereas circular polarization, the rotation speed is at the same as the frequency, so that sometimes causes some confusion. By the way, all this stuff, all this terminology actually came from optics. Faraday was playing around with a lot of this stuff. So Faraday rotation, they were far ahead of radio because they were doing optics. The human body doesn't have anything to detect radio as far as we know, but we have eyeballs. So, going back to Isaac Newton and even before, they had some pretty good feel for how optics works. And Faraday was amazing. A little side note on here. Everybody know what sucrose is? Everybody know what dextrose is? Why is it called dextrose? Dextrose from right-hand polarization. Now you think back in the 1700s, what were they thinking of making sugar water and running polarized light through it and seeing what happens? I mean, this whole mindset 200 years ago was far beyond our curiosity levels here, But, it's pretty amazing. I have great respect for alchemists. Yeah. Yep. It's a polar. Yeah.
Because the molecules are arranged in either left-hand or right-hand orientation.
Yeah.
And some you can digest and some you can't.
That's right. Left-handed sugar, when they're pushing that out, there's undigestible sugar that tastes exactly
Yeah,
like.
it tastes fine, but it's undigestible,
Yeah.
so theoretically, all it does,
Yeah.
if you don't digest it, you
Yeah.
just get diarrhea.
Yeah. So anyway, going back to lower frequencies now. Okay, so here we have let's see, what can I, oh, this is one thing which EZNEC does not have. So let's say we have a dipole that's slightly, let remove one of these dipoles. Let's go to a straight dipole here. And we'll remove one of these, and I'll show you the beauty of this particular program. Well, let's just delete that. So now we have a dipole floating in space here. Oh, I need to get rid of one of those feed points too. Yeah, when you remove the, there we go. Okay, so now we have a plain dipole and in free space, and our impedance is, I don't want the impedance so high. What did I do wrong here? Oh, it's, no, that's right, that's right.
Your links.
Yeah. Let's see. Let's do this again. Yes. Oh, you know what? Yeah, I was looking at the wrong orientation. So this should be minus 33 here.
Back on that sugar thing while he's doing it, when two molecules of the same atomic weight and mass are arranged differently, those are called isomers. And the Tinker Toys are put together in different directions.
Yeah.
So the sugars are exactly the same, except they point in different directions. And the
Yeah.
molecules are stuck together differently.
So one's right-handed threaded and one's left-handed
Exactly
threaded.
right.
So, yeah.
But the bolt weighs the same. And looks the
Yep.
same.
Okay, so we have impedance in the ballpark about 70.2 ohms here and minus 60.7. So let's show what's really cool about this modeling. So what we have to do, we have to change the setting here. So we are no longer going to be using the graphical input. So use a normal NEC editor here and we'll do it this way. So what we have here is the tabule, and this, if you're using EZNEC, everything's done this way anyway. EZNEC does not have the graphical input, although it will show you after it's already built. So what we have here is we have a wire, we have 51 segments, and we always want to choose an odd, yes? Yes it is, yes it is, yeah. You want to use an odd number of segments so you can put a generator exactly in the middle, otherwise there's no way of putting exactly in the middle here. So use an odd number of segments, 50 is a good round, 51 is a good round number. We have our same dimensions here, but what we're going to do is we're going to allow this to optimize the length to make it resonant. So what we do here is rather than our length here was, let's see, what am I missing here? Minus 51 next to, why did that not transfer over here? Okay, for some reason that did not transfer. Well, I'll enter it all manually here. Okay, so we'll build a new wire here manually here. So our X is, let's go to minus 33. But rather than putting a physical number in here, what we'll do is we'll put a symbol. So we'll put minus L. And we can use any number we want, but for doing the optimization, we put minus, let's put minus L. So I'll use a capital L here. And for the other side, we'll put an L. And let's see, the height really doesn't matter. We can put some arbitrary height here. Let's put a.
For X2?
I'm sorry, what's that? Oh, minus L? Did I put a? Oh,
On your X2, is it 1L or is it? Looks like IL.
oh okay. Let me fix that.
Not sure.
Minus L. Minus.
That's the other one.
Oh, let me.
The X2.
1, 2, 1, 2, 2. Z2. Oh, okay. No, the tags.
X2.
Oh, X2.
Yeah.
Oh, we want that. Oh, I
It
did.
looks like you have IL.
Oh, okay.
I think. It's hard.
It's,
It's
yeah.
impossible to see now.
Is that right? Well, let me just be sure.
Plus L. Okay.
Okay, that look
That
better?
looks better.
That looks better. Okay, radius of the wire, the thin wire. Okay, so now
That makes a difference.
that makes a difference. Okay, So we have, okay, so now what we do is we have our symbols, and we want to define our symbols. So we're starting with L as 33, a good place to start here. And, you know, I use a lower L, so it's,
Does case matter?
it should be, yeah, let's make this shift L equals 33. Okay, so that's our starting point. So we got a minus L and an L here. And we need to save this first and close this. Now we go to our calculate, and then we go to calculate start optimizer. And what we have is our L33. This is a variable that we're going to change. Now you can change any parameter there is, but if you're doing it at the same time, you can then use up a lot of computer space. So you only want to change one parameter at a time. So we click here. This is the parameter we're going to change, is the length. And what we want to do, these are the priorities. So what we're going to do, this happens to be set right. So we want to adjust the length so that the reactance is 0. So this 100 does not give you a number. What it means is 100% priority. This is our only priority. We can put different priorities on different numbers. But in this case, it's just a dipole in free space. We want to make this thing resonate. So we want to change the length of L. This is what the parameter that we can change. And then up here is the priority, and there's everything's there. So now we hit start, and what it does is it changes the length of the antenna and says optimize in 25 steps. So then we come back over here to our last number, and we have 34 feet. So it's actually 34 feet on the side, so it's going to be double. So it's close to 68 feet. And then so what we can do is we can update the file here, and now if we reload it, it will have the new dimensions on there. So you can do that with any parameter. You can even have like the angle of an inverted V. You can change the angle of that. And so it's, you know, that's one thing that EZNEC does not have. I wish this program had the NEC 5 engine. It would be, that would be the killer app. But I think it's already a killer app as it is. So any questions so far? Anything that anybody have a particular antenna you'd like me to model for you? Yes.
Yeah, just a question. What does EZNEC assume the wire is, copper?
It assumes copper, yes. Now,
So
you can
is there a
actually
way to
change
put-
it.
Is there a way to put different velocity factors in?
The newer NEC 5 does. NEC 5, and you also put the insulation on the wire.
Oh, wow.
Yeah. So, yeah, that's the latest thing. If you go to the EZNEC site there, Roy Llewellyn came out of retirement to...
I paid my $100.
Yeah,
20 years ago.
it just blows my mind that this is all free. I mean, you know, I've done enough software writing to realize you don't do that for free. So you know this is a real labor of love and Roy was just, I have great respect for him. He was actually helped write the actual NEC 5 engine, you know, which used to be, I got the license through my gang down in Wyoming, you know, it's like a $2,000 license. Now he's making that free too, you know, so. So yeah, please support your local or non-local developer. I mean, they are worth their weight in gold. You know? Yeah. Yeah. Well, it's you can do it. This also has a bunch of prefabricated antennas, which is kind of nice. EZNEC does too. So if we're just starting from scratch and we don't know what, well, we can go up to here, and we can look at all sorts of models here. We have HF collinear antennas, simple antennas, very high gain Yagis. You can actually build a parabolic dish here. That's a build function, so any kind of shape you want to build, like a grid pattern or anything, you can do that as well. I think EZNEC has that as well. Let's see. Well, let's see. How about a high gain VHF beam? Okay, so let's see here. Oh, it does have some parabolic stuff. If you do model parabolas, expect to hit enter, go and make yourself a cup of coffee and come back. There's going to be a lot of number crunching going on. Let's do a helix. Helix. Are you using any helix? You are. Okay. Here's a helix. Now, there's a magic number, and you probably know where it is the ratio between the turns where it changes from a axial do you know what that magic number is?
No,
oh,
you're absolutely right. As you compress or extend the antenna, you get a change in,
yeah,
in polarization and direction.
that's right. So we can do a far field on this guy. Non-vertical wire. What did they do? Ground recommended. Okay. Doesn't like it in free space, I guess, huh?
Well, that's that whole backplane.
Yeah. Well, there it is. Without it, okay. It's got some gain there. We can. Not too shabby. That's a nice pattern there. How many know that a parabolic dish has a back lobe? Did you always assume a parabolic dish had everything going over the front? But what happens when you hit the edge of a conductor with a radio wave? You get knife edge diffraction, and it bends down toward the back. So you have all the knife edge diffractions, which actually gives you a pretty strong back lobe off the back. Now, how do you prevent that? A tapered feed. You don't feed it uniformly. What you do is you get toward the edge of so your feed horn adjusts it so you don't have anything going toward the edge. So it makes sense. But you sacrifice gain. Everything's compromised antenna. Okay? Here's another thing. If you're building a multi-phase array with using this multi-elements, what gives you a cleaner pattern? Wide spacing or narrow spacing between elements?
In between.
Actually, the closer you are, the cleaner your pattern is going to be. You start getting more side lobes as you move farther and farther apart.
Oh, right.
But the gain of your main lobe becomes greater. So get a cleaner pattern, you move in. I worked on Tipsy 77 radar at Eielson. Had 172 elements, but it was close-spaced array because it had to be a clean pattern. You can't have side lobes when you're tracking military aircraft. But what's really interesting, the spacing was so close that the interaction between them radically changed impedance. So every of those elements had a 90-degree hybrid and a dummy load that burned up half the power. That's the price you pay when a close-spaced array. So they're actually dissipating half the power there with the reject loads on each of those dipoles. But HARP does the same thing. HARP was, when they were first building that, there was some hand wringing at the beginning and say, oh, we're getting a lot of, they were actually shutting down adjacent transmitters with the SWR trigger. So what do we do with that? Well, we could do with what the military said, put a dummy load on it, but rather than do, they put recirculators in each antenna and they feed that power back, not to the next antenna, but 2 antennas away from it. So now they don't dissipate that power, they simply feed it back where it's going to do them some good there. So very clever design. They did a lot of stuff right at HARP, It's just anybody been on the HARP tour? Yeah. I mean, they did so much stuff right, So anyway, we down in Wyoming, we are trying to avoid reinventing the wheel, so we steal as much stuff from HARP as we can. But we still have some clever ideas here. Okay, so let's go to EFWH antenna. Okay, and how do we do that? Well, we simply go back to our main antenna here again. Oh, let's open that back up. Let's see, what did we call that thing? Where did I can't remember where I stored that thing. Just simple. Is that it? There it is. Okay. So let us build an end-fed horizontal wire. Now, how many know that it's impossible to feed a wire exactly at the end? Let me change this to our you need another terminal. Otherwise, you're sound of one hand clapping, okay? If you don't have another terminal, you have a car battery and you don't have a ground end, okay? So you must have something at the other end of an antenna. Now, what we can do here is we'll look at our segments here, and we have a whole bunch of them, and more segments, generally the better, except you can make it harder to calculate. I'm going to do this in free space, and I'm going to move this down a little bit, just keep the thing things easier to keep on the screen here. So I'll scoot this guy down. Okay, so this will make this a little more convenient for me. And what we'll do is we'll take our feed point, and currently our source is on segment 36, about the middle of the thing. Well, let's put this thing on segment 3 instead, okay? So our source way near the end of the wire. Now, every EF-HW antenna must have a counterpoise of some sort. It doesn't have to be much, a 5-foot piece of wire hanging off the cold end of your transformer to do the job. But if you actually have it at the end, it's going to be almost impossible to match. Because the impedance, what's on an infinitely thin wire in free space, what is the actual impedance at the end? Infinite. You're going to have infinite impedance off the end because there's no place for that current to go through. So we could put it very close to the end, but not there, not there. So we'll do the far field pattern here. And just like where we feed the thing has absolutely nothing to do with the pattern, okay? Here we have our classic dipole design, okay? No problem with that. But our impedance here is a little bit unwieldy, okay? 1,588 ohms minus J, 1,135, okay? So we have an issue here. Now, see how minus that J is. No. Since we're at an end fed, we know we're going to be working with anti-resonance, okay? So to make this, since this is showing minus, which shows capacitive reactance, right? Minus J is going to be capacitive reactance. So what do we normally do with an antenna if we show capacitive reactance? What do we normally have to do? Do we have to lengthen or shorten it? You would normally have to lengthen it, right? Because the longer you go, you're going to lower the resonant frequency, and so as you lengthen it, you're increasing inductive reactance.
Oh, right.
But since we're looking at the anti-resonance point, if we stretch this out, somebody want to write this down, minus 1135?
Okay, minus 1135.
Minus 1135. So let us stretch this out. This is currently 68 feet. Let's go to 70 feet. And calculate this again. And okay,
Show you more than half did.
Yeah.
The imaginary part, anyway.
yeah, and see how much that changed with just really small change.
Yeah.
Less than with the impedance also.
The impedance changed some, but not as dramatically as as reactance. So just be aware of that. Doesn't mean you can't do it. You can't use it. Just be aware that, hey, why does this antenna work as advertised? Well, we have to accommodate the reactance, and that can change quite dramatically.
Yeah, that's interesting. So I put another one up not too long ago. I had it's basically 132 feet-ish
Yeah.
sloping, and I added about another 80 feet so I could try to get down to 160.
Yeah.
And one thing I noticed was I tried shortening it a little bit, and it changed dramatically.
Yeah.
And now I think I know why.
Yeah. Yeah. Well, the chart we showed right at the beginning, it tells you exactly why.
Yeah.
So there it is, right there.
Yep, yep.
Okay. Let's see. Here's the quads and loops and stuff. Okay. A cubical quad has what's about the approximate impedance of a quad antenna? About 100 ohms. Okay. Now, all the shapes of a quad, okay, assuming you have the same circumference, which shape is going to give you the most gain?
Probably a square-fitted,
A circle.
circle.
The gain is proportional to the enclosed area. So even though the circumference is the same for any given length of wire, the circle is going to give you more gain. And so you can approach that. There was some company actually manufactured cubical quads using loops there. They actually hung down like in hula hoops there, you know. And I forgot what they,
I saw one of those on YouTube or Twitter or whatever it was. Anyway, not very long ago.
yeah.
And I think it was for CB or so.
Oh, okay.
Yeah, but anyway.
What time we got here?
It is just about noon.
Okay. Well, so we're about halfway through. Want to go into the VNA? Everybody used a VNA? Everybody have one? Okay.
And now that I have a captive audience here, to let you know, after Eric is done, we're going to do door prize drawings. So if you didn't get any tickets or anything, then go see Charles up there.
Okay. Well, again, this is not the last word. Hopefully it's a first word for some of you. So we'll get my handy dandy VNA out, show you a few little tricks. Now, my first exposure to a VNA was a Hewlett-Packard Behemoth, which was about 45 pounds and about $1,000 per pound. I was working at High Pass. This does 99% of what that $45,000 instrument did at 0.01% of the cost. You know, just absolutely amazing, you know. So, you have VNA, and your standard 3-point calibration, which I recommend, is you first go to calibrate mode, and then you put put an open circuit and then a short circuit and load. Most of the time, unless you're going to be right at the antenna, I like doing the 3-point calibration with whatever cable I'm using. And the reason for that is, if you do this right, it doesn't matter what your length is. The whole point of 3-point calibration is to calibrate out your transmission line. So what we do here is, I'm not going to use the factory dummy load. I'm going to use one I can use a clip lead on. Okay. So same calibration procedure here, and we're going to, we won't have time to go into the two-port thing, but that's just another function which is just equally as useful for some of us, you know, designing filters and all that sort of thing. So what you do is you go to calibrate mode, and you want to keep this close together so it looks as close to a transmission line. Now, another thing about doing that is you can normalize your VNA for any characteristic impedance if you do this. How many are using open wire feed line? Okay, so if we calibrate, with the calibration procedure, you just calibrate with a 600 ohm line, and then everything's going to work right there. That's something they don't tell you. But now you all know that there's no comprehensive instruction manual for the manual VNA. You have to figure all this out online, but since most of us, or some of us old timers that played with the old time VNAs, you know about the calibration procedure and why you do it. But anyway, what we do is you hit calibrate, and by the way, there's a program. It's called Nano VNA Saver, and you can plug your VNA into it. I have a copy of it here, and you can do it. However, when you use that, you can no longer use the front screen, so it takes that over for you. But it gives you a plot of that, and I'll show you how that works at the end here. But for right now, we'll do the calibration procedure. So what we're going to do is, first of all, you do your stimulus. So you go between 3 and 30 megahertz. So you go to 3 megahertz. That's a good kind of a default, and stop at 30 megahertz. And that's a good thing. So we have an open circuit showing that over on the right there. But we're going to use our 3-point calibration here. So you go to back, go to calibrate, and I always like to hit reset after doing the calibrate. It isn't absolutely necessary, but it does help. Then we go to calibrate, and we do the open, and I have an open circuit here. Again, we keep them as close together as possible. Hit open, and then I hit short these together. And then hit short. And now I take my load. And the beauty of doing this at the end is it doesn't matter how long or how lousy this transmission line is or how many different impedances you have in between. If you do this calibration, it will tell you what the impedance is there, which is really, most of the time what we want. Now I just hit load.
Is that 50 ohms you have there?
That's 50 ohms, yeah.
Okay.
But you can do it for any impedance.
Yeah.
So if I have a 600 ohm one as well. You want to have them as non-reactive as possible. Now this is, you know, when you start going up to microwave and stuff, you're going to have to be a little more refined. But anyway, now we have a calibrated system, and whatever we put at the end of that will be correct. Okay? And so,
So you put up a dipole and.
yeah, they said a dipole that, and I don't know if you have any random wire over here. Maybe. Let's see. Let me see if we got. Oh. Ah. Hey, do you happen to have a wire stripper or a pair of dikes around?
We got one over here, Eric.
Oh, cool. Of course. Of
Steve
course.
apparently came prepared for any event.
Of course. Very good.
Well, that's
That'll
pliers.
do it.
That's pliers.
Oh, that's great. There we go. Official. See, it's, jamboree on the air. Be prepared, right?
Yep.
Jacket strippers still a little tricky. There. Okay, so I'll use a pair of wires in here. I'll use a orange and white one, I guess. Okay, so what we have just a random length of twisted pair here. Okay, and here we have a spiral, okay? So every time it goes half a turn, what does that tell us? What's half a lap? In terms of wavelength, what is that? It's a quarter wavelength, right? So every time it goes from one side to the other, we have a quarter wavelength. So we can count the number of turns and figure out the quarter wavelength. But what I want to talk about more than that, if we have a random piece of transmission line and we want to figure out what the characteristic impedance is, there's a very unique formula that works for the quarter wavelength. If a quarter wavelength transmission line, the input impedance to the output impedance is what's called the geometric mean. So if we have a piece of transmission line and we don't know what it is, we can do the formula, and what it is the source impedance times the load impedance is the characteristic impedance squared. So if we take those two numbers, and the way we do that is we take our VNA, we can look for a quarter wavelength. What we do is we take a transmission line, we adjust the frequency till it's a quarter wavelength long, and in other words, it takes one lap, okay? So we have half a lap around the VNA. We know our transmission line is a quarter wavelength long at that frequency. And now what we do is take the VNA, measure the impedance at one side, and then we short it out and measure it again. And now we multiply those together, take the square root, and that's our characteristic impedance. So any unknown length of characteristic impedance, so pretty cool. So, but it only works at a quarter wavelength, and it can only be a quarter wavelength at one frequency. Quarter wavelength Q section, again, is 100 years old, and they didn't have the math to describe it, but the guys putting the ZEP antennas on Zeppelins, the main purpose of which was to keep a wire a reasonable distance away from a gas bag the size of Milwaukee. And so the quarter wavelength transmission line there, again, converted the very high impedance at the end of the dipoles to a reasonable impedance for the antennas was fit. Most of the time was a link coupled, right? Anybody worked with link coupled antennas? Anybody have a Johnson Matchbox? Wonderful, wonderful device. I would like to go manufacturing modern matchboxes that have the work bands on them. You know, that's the only disadvantage of them. They didn't have the work bands on them. But so Anyway, I don't have time to demonstrate the two-port method, but one thing the VNA will do, and your average antenna analyzer will do, is a two-port measurement, where you want to actually measure through a filter. So the calibration procedures, pretty much the same. You do the normal calibration procedure, then you take a transmission line between you actually need two loads. So you have a transmission line between port 1 and port 2. You do what's called the through calibration, and then you do the isolation, where you put a separate dummy load on each of those ports, and then you calibrate that. And now you're calibrated to do all your measurements through a filter or anything else like that. So it's really good for doing. You can measure either the magnitude going through the filter. You can measure the imaginary component going through the filter. You can do that both logarithmically or linearly. If you're designing a filter there, you say, boy, this filter really looks lousy, you know, that doesn't sure. Well, you're probably on a logarithmic scale there, which compresses it. So if you want to see really what the filter is really doing, you know, if you're using it on a linear scale, you can see how good your filter can be. So anyway, lots of stupid VNA tricks, which are just amazing. Again, there's no reason not to have a VNA. They've gotten so cheap. I think I paid $60 for this. I think it even gotten less than that. Yeah. So, any particular questions on VNAs or anything so far? I'm open.
And just so you know, we're recording these presentations, so they'll be on the YouTube channel at some point, and you can go back and review. So.
Okay.
All right, marvelous.
Well, thank you very much.